Okay, good morning, everyone. So welcome back from the second half of the class. And today I want to continue the machine learning. In more detail. We just finished what's called the classification, which it's the model that gives you the class. For example, like the type of flowers or the type of dogs, pictures, and cats and things like that. But then there's another class of model that's probably very useful to what you are doing in terms of research, and also if you want to do like prediction in your manufacturing company, which is called regressions. So regressions is the model that predicts essentially number instead of classes. So if you are going to predict, I don't know, like just a number, like you want to predict, I don't know, like the cell of something, then regression would be something that you want to do instead of predicting classes. Okay, and I guess there's no better place to start with regression than the linear regressions. If you recall, like even though the same thing that we do with classification, we start with perceptron and also logistic regressions, and that is also a linear model. Same thing with, I guess with regression, you are going to start with linear regressions. But I think this one is, I think it's should be pretty straightforward to you, right? Because I think in your past experience, you must have done some type of regression with straight line before. So essentially, if you have the variable x, right? In this case, it can be, this one is just one x variable, but you can also have multivariate regression, which is multiple input, for example, but then your visualization would be more difficult, okay? You have x and you have the response, which is y, right here, right? And you were to plot the data on the graph. You can see that the blue dots are the data. And again, this one has some noises, right? So if you try to fit the straight line to it, then it's probably not going to be, 100%, touch all the points, right? But then I guess your job is to find the best fit to that, right? So before I go too far, I want to just mention that the equation for this, I guess one variable regression would be y equal W0, so that would be the intercept, so this value right here. And then there's also the W1, which is weight. So this weight is the same thing as you encounter during your classification, right? You have the weights that you're trying to learn in your model. Same thing when you construct this linear regression model in machine learning, you are going to try to find the weights, and the weights for the one variable problem would be W0 and W1, essentially the slope and also the intercepts to that. Okay, and the job for the machine learning model, or even your like a regular curve fitting software, would be to find the best fit to that. Okay. And also you can extend the same concept into multiple linear regressions, meaning that you have multiple input, for example, like x0, x1, and so on, something like that. Okay, but then the visualization would be more challenging in that way. Okay, so actually the problem in linear regression can be solved without machine learning, and I think you might have encountered the example or application of this throughout your career. For example, like Excel can do curve fitting with linear regressions, and behind the scene, it's actually solving this through the linear algebra I guess process. So the method to solve such problem is called the ordinary least square, so OLS. Okay, so essentially it's trying to find the best fit, meaning that it's trying to find it's actually the optimization problem again, but it's trying to minimize the distance between the data points and the line. For example, if you go back to this page, you can see that the pink line, which is drawn from the point to the straight line, the regression line, it's actually kind of like the error, right? So the idea is that the best fit line is the line that minimizes the distance between the blue dots and also the orange line, okay? And that method is the ordinary least square. And you can solve for that exactly, actually. You can solve for that with this kind of equation. And so essentially, it's a matrix process, like a metric manipulation process. But this one is actually quite expensive. Probably not expensive in a sense of if you only have one variable, but for the multiple linear regression, so this one can be quite, I guess, computationally expensive. As you can see that this sign right here. So that is the inverse of the matrix. And usually the inverse of the matrix can be quite challenging, and you can run into a lot of problems if your problem is not kind of suitable for solving. For example, if you have independent columns, that could be problematic to such algorithms. So, and this one you can go down the path of, try to solve this exactly, which there are many, I guess, theory or process of estimating such chess process, okay? But we're going to go through the same goal, but then using kind of like machine learning, right? And behind the scene, it's doing something, for example, like gradient descent that we talked about before, like this one right here. But there are also other ways of doing it. And also, once we do machine learning, there are also other tricks that we can do in order to estimate the line in a with various goals. Okay, and once we have the line, then we might want to see how good is our model, and that's called evaluation performance, evaluating the performance of the model. And for that, we can do a couple things. So first is the residual plot. And the second one is probably, the most commonly used one is the mean square error. And also this one, if you haven't used it, maybe you can consider using it to the coefficient of determination, or R squared, okay? So because I've seen, most of the work, from the student, they usually focus primarily on this. But usually I will try to motivate them to maybe consider this one also. And I'll explain what it is, okay? All right, so first, the residual plots. So this one, it's also, it's a plot of what's called residual, okay? So what is the residual, okay? The residual is the difference between what the model is predicting, so this one right here, y predict, and what's the ground truth, or the actual value, okay? So if the residual is 0, so that means your model is predicting, perfect data. So it's I guess, best accuracy if there's no residual. But probably that's not going to be the case, right? So you're going to try to, I guess, first you can, if you look at the residual plot, you can kind of see the magnitude of the residual. So if it's like really, really high, then that's something alarming about your model, right? But another thing that we can do is actually we look at the shape of the residual. Okay, so not just the magnitude, but we can look at the shape or the trend of the data if there's a pattern to it. Okay, so and that is kind of powerful in a sense that if you were to plot what's the residual on the y-axis right here, and then you're going to plot the predicted value right here. Okay, so essentially you are looking at the value that the model is predicting versus the error of that value, okay? So essentially, you're looking at, I guess, how wrong it is, each at specific value of your prediction, right? And I guess what you are looking for is actually the value that's not too high, right? Because if the residual is too high, that means your model has a lot of error, so that's the first thing. But the second is that try to look for the pattern. So for the best scenario, it would be if it's randomly distributed in here. So for example, if your model produces a residual plot that looks completely random, like all the dots are just scattered around kind of equally, so that means that these are all the noise. So you're essentially plotting the noise, which is good. What you don't want to happen is exactly something like this. Like exactly like in the example. In the example, you can kind of see that there's a trend like this, right? So this trend means that if means that your model is actually predicting more error at the lower values, but it's predicting less error at the higher value. If you see the trend like this, so that means that your model is actually not capturing the useful information from your data, because you are seeing some of the trends that should be in the model, but it's not in the model. It's kind of exhibit itself in the residual. So that's not good. So you want your model to capture all the useful patterns, but kind of leave all the noises to the error. So if all the errors are noises, that's good. So what you're looking for is the residual plot that's more randomly distributed. And so for example, if I see something like this, that means that if you're using linear regressions, try changing it to something else more complex. For example, you can use polynomial plots, or you can use other machine learning model that we're going to cover in today or maybe next week. Okay. Okay, so the residual plot is quite useful, as I will show you later. Also, another commonly used one is the mean squared error. So that is pretty, I guess, self-explanatory. So you are plotting the difference between the ground truth and the prediction, right? So essentially, this one is also the residual, right? Right. So you're just plotting the residual squared, okay? But then you are plotting, but then you are summing, over your observation. So you're summing the square of the residual over all the observations, and then you divide it by the number of your observation. So that's what the name comes from, right? You are summing the squared error, right? And then you're taking the mean, meaning you're summing over the observation and divided by the n. So that's the mean part, okay? So MSE, it's kind of a general things that you can show, because essentially if your MSE is low, that generally means that your model is good, right? If it's large, then there's something you need to kind of take care of it, okay? But again, this one is kind of a bird's eye view of your error, right? It doesn't show you if your model is actually complex enough or if you are actually not capturing the useful pattern. So that's something that you might want to look into the residual plot, okay? Another thing that you can do apart from MSE is called the coefficient of determination, or people like to call it R squared. I'm sure you have seen R squared before. Essentially, it's the measure of the proportions, okay, of the variance. Okay, so how things are changing for your dependent variable or y value, all right? That can be explained by the x variable, okay? So I know that this one doesn't really mean anything. Like it doesn't mean anything to me either, right? But what I want you to kind of have some idea is actually something like this. So your R squared, right, can go from 1, right? Or I guess it can go from 0 to 1, okay? So let's think about it, right? So the R, maybe I should tell you the equation first, okay? So R squared can be calculated by 1 minus, this is the sum of squared error and sum of square total, total sum of square, right? So the top one is actually the residual square. So it's actually, this is MSE, right? The whole thing on the numerator, I think it's on the numerator. The upper one is actually the MSE, right? The one at the, I guess that's the denominator, or the one below, okay? It's actually the sum. It's actually the ground truth minus the mean. So that's just a total sum of squares. So like how much is your data actually fluctuated from the mean, okay? So like your total fluctuation. So it's actually, this part is MSE. this part is called like the total fluctuation of your data. So that's why people like to call it, in another word, it's called scale MSD too, okay? All right, so another thing, if you work it out a little bit further, you can see that this thing actually go into the variance. So it's actually the variance of y. So it's actually MSD scaled by the variance of y, and then you take the subtraction of 1 over that, okay? Okay, so the equation might not mean much, but I want you to have some intuition of what it is, right? So r squared can go from 0 to 1, okay? So let's think about the best scenario, like if your r squared equal to 1, what does it mean, okay? So it means that your MSE, right, so your error is equal to your variance, right? So sorry, not equal to variance. That means your MSE equal to 0, right? If you are equal to 1, so that means that this part needs to go to 0. Or in other words, your MSE equal to 0, so your residual go to 0, okay? What happens if your r equal to 0, right? When r equal to 0, so that means that your MSE is equal to the variance of your data, okay? So when r equal to 0, which is kind of like the worst case you can do, it means that actually all of your useful fluctuation or pattern in your data goes into your error, right? So, and in that sense, so maybe I can have another situation where it's 0, 0.5, and 1. Okay, maybe that will be more a better explanation, right? So when r equal to 0, so that means that your MSE, so your error, it's actually equal to the variance in your y. So that means that all of the changes in your y variable, it's actually going to your error. So you're not capturing any useful information or pattern or anything. Everything's going to error. So that's the meaning of r equal to 0, okay? But when r equal to 1, so that means that your MSD, so your error equal to 0. So that means that your model can capture all the variation in your data, okay? Which, I mean, it can be good, and it can also be bad too. When it's bad, it means that if your data is noisy, that means your model is actually capturing the noise, which might not be something that you want. You can overfit your data. R squared just means that all the variation is taken care or included into your model, okay? So what happens if r squared equal to 0.5, right? So that means that half of your variation goes into your error, and half of the variation in y is captured in your model. Okay, so that's essentially what it means. So essentially, you want to shoot for r squared that is high. But the thing that I like about r squared is that you can have a model with high r squared, but it's actually not capturing the right variation. For example, I don't think I can draw something like this in right here, but maybe I can find the example of it from the internet. It's actually better. But there's actually a case where your MSE is low, but your R squared is actually, when your MSE is low, but your R squared, it can be high or low. And that's actually quite telling in certain situations. Okay, maybe I'll get back to you on this in the actual example, and you'll see that R squared is actually quite useful. Okay, but so in our example, I guess in our example in the class, I will show you all of it. So MSE, the residual plot, and also R squared, so that you can kind of see what's how the values are changing when we change a model. Okay. All right, so let's go to the exercise. So we're going to perform simple regressions on the kind of like the famous data in machine learning regressions, is housing data. And then we're going to do some of the data exploratories to histogram, pair plots, and some of the correlations. Okay, so let's go. Okay, so we're going to go to our code. And let me pulled up my new files right here. So maybe c2.ipynb. Okay, so let me just copy some of the starting point for my code. So again, this part, it's also the utility for plotting and things like that. I don't want to be writing a lot of the same code all over. Okay, so importing, try to run it. It's good. Okay, everything's working. All right. And in here, I guess I'll just import the whole thing. I'll just explain to you what I'm importing. Panda, NumPy. JSON is actually for reading some of the raw data from the input. And you've been through a train test split already. This one, it's a utility function from the other folder that I wrote myself. And the one that we're using to build the model is actually the linear regressions right here. So that's the first one we're using. And also we're going to use another model called ransack regression, regressors, I guess, later on. Okay. So let me load the data. Okay. Right here. Okay. So the utility part is actually the variable that I define up here. So that's nothing. I guess it just gets defined on the top of your code. So let me just run the whole thing. See if it's reading. Okay. So let me know if it's not working for you, because maybe some of the path might get mixed up. If that's the case, let me know. Okay. All right, so let me just show you the data real quick, right? So we're going to do df just to see. So the data is actually the data of the house price, okay? And I think I do have some explanation for the data right here. Actually, so sorry, I'm actually copying the wrong one. So let me do that one more time. Oh, okay, it's right here. So the housing data, right? So I guess the x value, there's a x and y values in your data. So the x value is actually all of the attributes that's pertaining to the house. For example, the town, the residential land, or like the concentration of like nitric oxide, so like how good the pollution around the house. And I think there's a size of the house, right? And the thing that we are looking at is actually the y value, right? So this one, wait, where is it? Yeah, so MEDV. So actually that one is the y value, right? So the x value is all of this. So in this example, the data is a multivariate model. So you have a lot of x and one y values that you want to predict, okay? I just forgot the abbreviation for a second, okay? And I think I want to recopy again because I used the wrong file, okay? But I think the first one the same, and this one, yeah. Sorry, you might be confused. So it's actually this one. So I haven't loaded anything yet, actually, okay? And then I'm gonna load the data. Okay, so that looks more like it, all right? So as you can see that all of this actually are the x value, and MEDV is the y value. So this is the price of the house, but then multiplied by 1,000 US dollars. So for example, the first one, the price would be like 24,000 per square feet or something. So it's pretty expensive, okay? All right, so the first thing before we do anything, we should explore the data. And Panda is actually allow you to do a lot of this pretty easily. For example, I can do histogram to see the actual magnitude of your variable like x and y. Like you can do df.hist, so that is the histograms. Okay, if I were to do that, you can see that the figure is a bit small. So let me just give it the argument fixed size equal to 10 and 10, so that means it's 10 by 10 inches. Okay, so if you look at the histogram, you might want to check out for example this the range of your data. It goes from like 0 to 100. Does that make sense? Okay, and if there is any particular like outliers that you want to take care of, and if there's any anomaly in your data, for example, so you can I mean, this one is pretty clean because this is a toy data, but in real data, probably you want to clean your data to like get rid of all the outliers and maybe incorrect values, for example. And also, this is a y value. You can see that it kind of ranges around, like from like 1,000 to maybe like 50,000, like 50, so $50,000 per square feet or something. Okay, and again, we can kind of look into a bit more by using another library called the Seaborn. So I'm just going to show you that if you do this one, then you can start to plot the histogram in a more detail, right? So what I'm using here, I don't think I showed you before, but SNS is another visualization library, very popular in Python. Let me just show you the website first. Okay, Seaborn. Okay, so this one I think it's quite pretty. So and it's quite easy to use. So if you like the plotting style in this I guess library, you may use it. And I've seen a lot of paper using Seaborn nowadays instead of just the pure like the matplotlib version, which look kind like this one is from the matplotlib library. It looks quite boring nowadays. So you can use Seaborn to make spice up your publication a little bit more. So I guess if you see the syntax, it starts with SNS, which is something that you import from the top of your code. So right here, import Seaborn as SNS, right? And then you can start using it. For example, if you want to do the histograms, you can do sns.histplot, okay? And the good thing about Seaborn is that it works very, very well with Panda data frames. So you can do a lot of cool things. Just plug in it, like just give it the data frame, give it some attributes or arguments, and there you go. You have a lot of graphs that you can kind of plot, right? Something like that. Okay. So here I'm plotting the histogram between the of the LSTAT and MEDV. But you can certainly do more. For example, if I want to include another column called CRIM, then I can just type it in here. For example, I can just add more column name, CRIM, and then I can just run this one again. And now I have 3 graphs in here, okay? And it even have this kind of like a density, like it's called the density distribution of your data too. It's kind of nice, okay? And what you can do is also you can change the number of bins. If I change bin to maybe 10, then you can see that the number of the bars decreases. Okay, so you can play around with the number of columns and also change the bin. And also, if you don't like this like a density distribution graph, then you can say KDE equals false, and then it won't print that one. So I do recommend if you want to go like plot something that looks prettier than just a standard Python library, then use Seaborn. It's actually quite nice. All right. So the first thing pretty straightforward, right? So the next thing that you can do is actually do the pair plot. So this one Seaborn is particularly useful. Let me show you this one. What? I need more. Okay, this one. Okay, so essentially, I want to do the pair plot. So let me just show you what it is first. So see, it's such a simple command that gives you so much more, a lot of information. Okay, so the pair plot, it's what the name suggests. It's the plot between the pair of variables. For example, if we were to do this one right here, right? So you can look at the y-axis. It's called index. So that's one of the x variable. You're plotting against different things. You're plotting against LSTAT. Okay, so pair plot is actually just pick 2 variables and plot them against one another. Like pick a bunch of variables, like just maybe pick all, like give all the pairs, like all the combinations of all the pairs, and just plot them together. Okay, so why would this be useful, right? So sometimes when you look at your data, sometimes you might not see the correlation between your data, right? It's kind of hard to see, what is the correlation between your data. And correlation can be useful when you are picking the right variable to use in your model, okay? So this one is useful because it allows you to basically just do this. If I want to predict MEDV, like this one right here, so because this one is the house price, right? I want to see what kind of correlation, like what other variable correlates well with MEDV. And that's the variable that I want to use to build my model. Like usually you will have a lot of variables, but then not all of them is actually useful when you are building your model. And the pair plot is actually quite nice, okay? So what you want to do is that, like if you see something that has trends like this, that means that you might want to pick this variable to include into your model, right? I'm actually inspecting the last column, right? So this one, what is it? It's PM. That's pretty good, right? If you see something that looks, oh, this one's pretty good, see? LSTAT, right? It looks like it has some pattern to it. If it's like random, maybe if it's like this one, then maybe you don't want to pick it because that one is, it doesn't correlate with your Y variable. So that's a useful clue to know if like what kind of variable you want to include in your model. Right? And I like it because if you don't have many variables, then you can kind of see all the correlation between your data, right? But as you can imagine, like if you add more to here, then you'll start to have like bigger and bigger figure. It will take longer and longer to calculate. Let me just show you. If I were to create adding just maybe 2 more. Okay, I want to add maybe B and text. Okay. Let me just add 2 more, B and text, right? You're going to see that now it's getting quite a bit difficult to, I guess, take longer to calculate, right? And then it's kind of too much to see too, right? So at some point, you're going to have to find another ways of doing it. But essentially, the pair plot is actually quite useful. Okay? So do play around with it. So or maybe you can just reduce the number of it by just deleting the column names. And in that way, it's much easier to look at like that. Okay? Okay, so looking at the pair plot is actually quite detailed. But wouldn't it be nice if we have some type of a matrix to measure how much things are correlated, right? And then we can use that number to make some decision if you start to have a lot, many X variables. And that's exactly what the correlation measure is going to be useful. Okay, so we're going to go back to our lecture, slides, and correlation, ความสัมพันธ์ นะครับ Okay, so when you say something is correlates, it means that when something change in a certain way, the other thing kind of change too. That's called, or another way of saying it's like that you have some relationship between your data. When something goes up, the other thing goes up. That's correlation. Like you have some more, I guess, non-zero correlation. Or you can even have something like anti-correlation, where something goes up, the other thing goes down. That also is, that kind of behavior, it means that your data is actually correlated too, but in an opposite way. Right? That's correlation, okay? So it's the relationship between 2 random variables, okay? When you say something about relationship, you can say that it kind of, like when something change, the other thing change, that's relationship. But it doesn't say anything about causal, okay? Causal, it means that something is causing something to change. And you cannot use correlation to imply causal. That's kind of dangerous. Like, and maybe that's very tempting when you write paper. When you see X and Y and you see the graph goes up, you might say that actually X is causing Y to go up. Actually, that's wrong. You can only say that X and Y are correlated. It has relationship. Causal relationship is actually come from domain knowledge. You have to know like in your domain knowledge. If actually X, for example, if X is the level of insulin and Y is like your blood pressure, and you actually know from your medical expertise that that is a causal relationship, that's something that you can make summary about from the domain knowledge, but not from the correlation measurement. So be a little bit careful when you interpret your results from your graphs, right? But correlation is extremely useful when you are trying to build the regression model, because when you choose your variable, you do want you want the variable to have correlation between one another, and because that will be something that you can build like a good model from. Okay, and the commonly used measure of the correlation is called Pearson's correlation coefficient, or R. Okay, this guy right here. There are other ways of measuring correlations, and I guess if you have specific requirements in terms of your relationship, you might want to look at something else. But in my experience, I never use anything else apart from R, so you should be suffice. Okay, so what R means? Again, we should try to understand the value of R, right? R, but not R squared, or different things, right? So first, if R or correlation equal to 0, right? That means that your x and y does not have any relationship. As you can see from the diagram or the picture, the green dots are randomly distributed, so no correlation. If the variable have no correlation, you don't want to include this variable in your model. It doesn't help your model. It's just noise. Okay. But as you can see that as the correlation goes up, right, 0.5, you can see that the trend start to emerge, right? And then if 0.9, you can see that the trend seems to be stronger. And when it's 1, it's perfect correlation. So one goes up, the other one goes up perfectly, right? This is a positive correlation, but you can also have the negative correlation, which is the opposite, which is something goes up, the other thing goes down. And the magnitude of that, it's the indicative of how strong the trend is, or how much noise are there. So 0.5, you still see some noise, but then when it's -1, it's the perfect negative correlation. Okay, so that's something that we can use in order to determine, what you want to include in your model. And the number is nice because you can write logics on it too. So you don't have to kind of look into the pair plots and have, I don't know, just kind of have a feeling, like use your like visual judgment. Like you can use the number as the indicator for your selection, right? Okay, let's do just that. Okay, if you want to calculate all the correlations, the code is pretty involved. It's, you have to like do the loop, pick all the variable, and do a lot of. I mean, it's doable, but in Python it's extremely simple. Like it's incredibly simple. It's just one line of code. That's it. This one, just one line. This is how you do the correlation in all of your variable, right? So let's do that. Display core. Wait. There you go. This is it's incredibly simple. Like, I mean, it's very, very quick to do in Python actually. So what you're looking at is a correlation between the two variables in your data. So let's see. CRIM is one of the variable, right? How does it correlate with itself? 1. So the same variable should have perfect correlation with itself. So as you can see that there's a 1 along the diagonal. So that's what it means. The perfect correlation with itself, right? But then once you look at the off diagonal value, you can see that the magnitude is less than 1. And the closer to the magnitude of 1, the more correlation between these two variables, right? And as you can see that these are symmetrics, right? Because the correlation between Cn and so maybe you can do this one, right? Usually it's symmetrics because the correlation doesn't really depend on directions or anything. There's no prefer direction. So usually you just see the upper or lower triangle. That should be enough. Okay. So I mean, from this data, you can kind of skim through to see if there's any correlation between your x variable and your y variable, right? Because your y variable is right here, MEDV. So what you want to do is actually scan through, like the last column to see if there's anything that you might want to get rid of, right? If you want to do maybe like 3 or 4 variable, you can kind of pick the one with the highest magnitude, right? Something like that. Okay. I mean, this one is good, right? Number is good, but maybe there's even like a better way of presenting this to your advisor, right? Let's do that. The seaborn is pretty cool. Let me show you. This one. So this one looks a bit, takes a bit longer, but you can just copy my code too, right? There's nothing wrong with that. So let's do it. It's called heat map. Right here. Pretty cool. So seaborn is pretty nice. Everything kind of look pretty, like all the color are more like pastel color. The fonts and like everything looks more modern with seaborn. Okay, so what you're looking at is actually the same information as you just look at the number, but this one is plotting nicely, so you can show this in your paper too, okay? So what you're looking at is the correlation, but then I guess we only need the triangle, so I do the lower triangle, right? Take a note with the color though, right? The color that goes to red, it's a positive correlation, and the blue color is negative correlation. But actually, I guess the darkest red is actually not 1 because the data is actually going from like 0.2 each to like negative 0.7. So take a note that when it's the darkest, either for red or the blue, it doesn't mean perfect correlation. It's just that the range of the data only goes so far. Okay. So again, we can kind of look into what variable you want to use in our model. So we want to predict MEDV, so that's the house price, right? So you want to scan through which one has the, I guess, highest magnitude, right? So in our example today, we're going to use just one variable. So what do you think I should pick here? Because today I want to choose one variable for simplicity, right? What do you think I should choose? Just one x for me. Scan through all of this and tell me which one's the highest magnitude though. This guy right here. Right? Do you agree or not? Okay, when I say highest, I mean the highest magnitude. Doesn't matter if it's negative or positive, but you want the one with the highest correlation. That's your best bet when you choose your model. Like you don't want to choose this guy, like this guy, like this one is the worst. Like if you try to build your model with this model with 0.18 correlation, your model is going to be noise. You're just predicting noise. You're not predicting real data, man. Okay? You want to use the one. So for example, like if you're in your research, you might have like 100x. You want to choose maybe 10, then yeah, correlation. Yeah. Okay, so that's why from now on, when from each exercise that I show you, I only choose one example, one x, because I want to plot. I want to show you the plot of the plot. I want to choose LSTAT to predict my house price. Okay, and if you go back to see the pair plot, you can kind of it does make sense, right? Let's see this one. This one is the pair plot between LSTAT and the house price. As you can see that it's actually have pretty high trend, right? Maybe the second one that you might want to choose, it's let me see. If we go back to my heat map, you can see that the next one in our candidates would be RM. RM might be okay, and if you go back to look at the pair plots, might be okay too. RM, where's RM? Right here. Wait, oh, actually I just commented out, right? I need, maybe I'll just do LSTAT RM and also MEDV. like that, right? So RM and MEDV is right here. See that one? So that one is a pretty good candidate, right? But another thing that but once you start to select more than one X, another thing that you have to kind of beware is that you don't want your X to have a lot of correlation between one another. So that's the thing. If your X do correlate with one another perfectly, that means you have the, what is called the linearly dependent columns. And that's going to affect how good your model is too. So if you were to choose RM and LSTAT as your X, then they do have some correlation between it, which is not ideal. But sometimes, in real world, it's probably very difficult to find all the X that actually are, like have no correlation to one another, right? Something like that. So keep in mind when your data is more complex, okay? All right. So, but this one just to keep it simple, I'm going to use LSTAT as the only X variable for me. This one, nope. Okay. So, okay, moving on. So I'm going to extract the data, okay? So in order to extract the data, I just have to just use this one, right? So I want to change everything into the NumPy array. So the value, make it so that all the Panda data frames become NumPy array. Sorry, right here, okay? If I were to inspect what X and Y is, right? X, well, this is essentially just one column, essentially. It's actually two-dimensional array, but just one column. So I can have more X, which is, if you want multivariate models, then you can choose more X, but it's a two-dimensional, it's like a matrix. But then for Y, it's essentially just a vector. This is just a one-dimensional array, okay? Okay, once you have X and Y, then you can kind of see that the process is the same as what you had before in terms of classification. So you want to split your data in test and train data. So why don't we do that? Okay, right here. It's actually, this one is similar to how you would do classification, right? You use a train test split with the X and Y in it. And also the test size is equal to 0.3. So that means you are reserving 30% of your data for testing. Okay, and then the random states, it's just telling that, it just make sure that everyone has the same randomness, like the same random number generator, right? And then the results, it's actually all of these 4 variables right here. Okay. Okay, maybe I'll just check your data real quick. How, like, what are the size of this, right? I can do xtrain.shape to see. So for your training data, you have 354 rows of data. And if you do xtest.shape, then you can have 152 rows for testing. Okay. All right, so the data is ready. Let's build the model. Okay? When you build the model, same thing. You are loading the class definition from the scikit-learn library. So I think let me just copy this one. Okay, so sklearn .linear model. So that's the module, right? And you are loading the linear regressions class definition, right? But this is the definition of the class, but this is not the instant yet. So what you want to do is you want to what's called instantiate the object. So linear regression, and then use that. It's almost like a function. It's actually calling the constructor function. Okay, I'm gonna put the results into a variable called SLR. Okay. And that's it. Linear regression is extremely easy because there's not many things that you can, that you can customize. If I were to go to linear regressions in scikit-learn documentations, I don't think there's anything much you can do except from maybe like random states or something. So let me check that real quick. See, that's it. That's only a couple of things that you can do. So that's very, very little things that you can customize. So that's why I only do just the default values. Okay, so just parentheses and close it. Okay, so nothing else to do. So the model is instantiated. So the next job is to fit it to your data. So, okay, so what you want to do is actually to do X train and Y train. Okay, done. Okay, so when you're training, right, what you are doing is you are finding the best value of weights, right? As you recall, when you look into the linear model, there are two weights in here for a single variable model, which is the intercept and the slope, right? So let's just check it out what it is, okay? If you want to see the weights, then it's SLR, so that your object dot COEF and then underscores. There you go. So that's the slope. So the slope is 0.9. So that means that it's actually the house price is actually inversely proportional to your x variable L stat because the slope is negative, right? And also SLR dot intercept underscore. That's the y-intercept. So that means this is 34. So when L stat equal to 0, your house price is 34. I don't know if that makes sense or not, but that's what it is. Okay. Okay, but actually that's one is kind of in the model itself. You don't need to. You need to care about it if you don't need to go into detail. But what you want to do is actually you want to see how good the model is, right? So let's test it. Okay. When you want to test it, you want the model to predict your test data. So you want to do slr.predict. See, similar things to what you would do in your classification. I'm going to have it predict. Well, in here, I'm actually predicting both the test and the train data. So we'll do both, okay? Y train, predict, right? So you can certainly have the model predict the training data, right? There's nothing wrong about it. Right, do X train, right, and then I can do Y test predict dot predict, right, and then X test. Okay, I think that's the one. Okay. Again, if you were to look at the prediction, for example, Y train predict, you can see that the prediction is a number. So this is regressions, right? If you were to use classification model, you only have integer like 0, 1, 2 as your prediction. Now this is a number with digits. Okay. Again, if you look at the y-test predict, it's the same thing, right? It's just a number, but just a different size of it. Okay. Okay, so let me just do some plotting. Okay, because when you have only one x, it's pretty easy to plot, and you can see how well your data fit your model. That's kind of nice thing about this example, okay? So in order to do that, I'm going to use my utility function called plotRes, which I declare it right here on the very kind of like the second box in here, plotRes, so plot the residual. Oh, no, actually plot rec. So this is the plotting the model itself, and then I can plot the residuals too. Okay, so let's do just that. So this one is a function that I wrote myself. So there's nothing universal about it. It's just that I designed it this way. Okay. Actually, I might just gonna copy it because the input is kind of long. So let's do that. Okay. Let's see. Okay. There you go. So what you are seeing is the raw data. So I guess the left figure is the training data, and the right figure is the testing data. right? 70%. And the black line is linear, the model. It's a linear model. It's a straight line, right? That fits into the data. So as you can see that it's, it's doing the best it can, right? I mean, you only have linear function. So yeah, so that's what it is, right? So how it compares between those two, right? Okay, so I guess visual inspection is nice, but keep in mind that once you have more than 3x, you cannot do this anymore. There's no way you can visualize this, right? So this one only because you only have 1x, right? But no matter how many x you have, you can always look at residual. There's nothing prevent you from doing that. So residual is very useful, okay? What I want you to kind of notice from this fit is actually, I want you to kind of guess what the residual looks like first, okay? So let's see this. When the value that I'm predicting, it's, I guess it's low, right? This is when the value is low. The y value is low. I think the model is doing okay, right? It's fitting the data, it's pretty good, right? But when the y value is high, I think the data, the model is not fitting very well because there are some high data. Maybe I should use the mouse so that you guys can see from the video, right? When the y value is high, I don't think the model is doing very well because like the model is actually not capturing all of these points right here. You see that, right? It's actually capturing the points pretty well here, right? But not here. So what I would expect from the residual is that it should have low residual or maybe less patterns when the y is low. But then when the y is higher, you should see some pattern, which is higher residual. And that means that your model is actually not good enough, right? Like if you from visual inspection, you can see right away that this one is not good enough for your data, right? Because if you want your model to kind of capture this portion right here, then it's kind of need to curve up. Maybe like parabola would be something more appropriate, right? But then you don't have this luxury when you have more than 3x, right? So, but then residual plot is actually going to tell you right away that your model is not good enough. Let's see this. There you go. Okay, so as you can see that the model, like even if I just told you from my visual inspection, it's actually not the most accurate representation of the residual, right? So the residual that you're seeing, so on the left side, you can see that it's actually higher when y is low. So it's not even capturing the pattern, the right pattern, at the lower value of y. It's actually doing okay at the middle portions, but then at the higher portions, at the higher y value, it's not capturing again, right? So as you can see that there's like this trend right here where it goes like up, and down. So that means that your model is not capturing the useful information. It actually exhibits in your noise. So your job is actually choose better model from the residual plot. So then this one, you can always do it regardless of how many x you have. So keep that in mind when you're building your model. Okay, not just MSE, right? MSE is too crude. It doesn't tell you much about the quality of your model. I mean, it does, right? I mean, it does, but it doesn't tell you like where you should go from here. I guess that's the thing. Okay. All right, what else do I have? Okay, so R square and MSE. Okay, so something that you always want to do. In terms of calculating the MSE, there's already a utility function from scikit-learn. As you can see that I can import it from here, mean squared error, and also R square score. So R square and MSE can be calculated pretty easily from these two functions. Okay, let me do just that. Okay, maybe I can just type what here. Okay. It's called mean squared error, and all you need to do is just putting in the actual value and the predicted value. So y train predict. The order is not important. You can put the prediction in front. It's okay because it's always square. So it doesn't really matter the order, right? That's it. It's 37.9, right? And then if you want to see the R squared, it's R whole score, right? Y predict, Y test predict, right? You want to do, actually I want to do the R square for the train, the train one first. So Y train and Y train predict, right? So that's the training data. So 0.5. Okay, so the thing about the MSE and R square is that when you look at MSE, like you don't have any idea like if this is large or small. It's just a number. Like usually when you do MSE, you want to compare between different models. But if you were to start off, building your model, if this is small or large, like you have no idea, right? So MSE is actually not a good model when you're building them, not a good matrix when you're building the model. It doesn't tell you if this is large or small. But if you look at R square, for example, you see 0.5. So that means that you are not capturing the pattern because the half of your variation actually goes into your error. You're not capturing lots of variation. So that's what 0.5 means. Like only half of the useful variation or noise in that sense goes into your error. So that means that you need to do better. So R square is a good indicator for that. So I would say that look into both residual plots and R squared in order to see if you need to do something else with the model. But then when you are presenting everything together, then maybe you can use MSE to compare, to choose the best model. Yeah. Okay. So this one is not doing great, which is kind of understandable, right? It's only a linear model. Okay. Okay, so you can see here that I'm actually doing both the training and the testing data for MSE and also calculating the R square for the train and the test data, right? And here's the thing, I want to collect all these results into a nice data frame so that when I presented it to you, I guess you can compare it in an easier way. So what I want to do is actually, I want to collect everything into the dictionary, and then I actually input that back into the data frame, and so that when I display it, I can it become tabulated. Okay, so let me do just that. So this is, for example, like when you are doing things in Python, like thinking about how you collect the results, it's actually quite useful. Like if you have a way that you can systematically collect the data and put into the table. And it's kind of nice because in the end you can just export it to Excel and it works, and it's just rerun things automatically like that. Okay. So for our first model, simple linear regressions, we are I guess I can use R square as the benchmark here. So we go to about 0.5. That's the first benchmark that we have. Okay. Okay, so that's it for the linear regressions. Maybe we can take a couple minutes breaks and when we come back, it will be faster from now on because you already see all the, I guess all the trends. Oh, before we go, from all the flow that we do, right? Starting from like X and Y, remember like going to maybe something here, you get all the data. Okay. You extract all the data, right? From this point and down to the end. There is actually one step that I ignore compared to what you would do in your classification. Can anyone guess what it is? Yeah, standardization. I intentionally ignore standardization. And the reason is that if you only have one X, it doesn't matter if you do it or not, because the standardization is only there because your X is, have different range. Like one X could be smaller in value, the other one is higher in value. And I say that you standardize because you want those two X to have the same importance But if you only have one x, then there's no point doing it. That's why I skipped it. But I will show you later on, if you do multiple regression, then you do need to standardize your data, or else your model is gonna only focus on the x with large values. Okay, good job, thank you. Okay, a couple minutes breaks and we'll come back and continue. Okay.